Okay, well, welcome everybody. It's my great pleasure to introduce Rama Govindarajan, who is the Kirk Distinguished Visiting Fellow in the Turbulence Program. Rama got a PhD from the Indian Institute of Science in Bangalore, postdoc at Caltech with Tony Leonard, who might be here or might be in the audience on Zoom. Welcome, Tony, if you're around. Rama is now a professor in the International Center for Theoretical Sciences at the TIFR Institute of Fundamental Research back in Bangalore, so back in the hometown. Her research interests are instabilities and the transition to turbulence in flows with viscosity or density variations, particulate flows with and without phase change. And her title today is Mammatus, Clouds and Sedimentation Instabilities. So thank you very much.
Thank you, Rich. And this visit to the Newton Institute is going amazingly well. So I am deeply grateful for the Kirk Fellowship, which made it possible. And I'm, of course, grateful to all collaborators who've worked with me over the years. Okay, so I'll be talking about two kind of different things which look unconnected, but I'll try to explain how they're both relevant in similar situations. So the first is sedimentation, namely rain, precipitation of little droplets coming down from a cloud base. Can you see those blue things? Is it visible at the back? Yeah. So basically raindrops falling out of a cloud base. This is actually the anvil of a cumulonimbus cloud, which was, it's a real photograph taken by an astronaut from space. So you can see how flat these anvils are. We will come back to that. The cloud is somewhere here rising from the ground up there. And so what is a cloud really? So a cloud is mainly air, like it's a huge percentage of a cloud is just air. It has water vapor, which is about, max like 1 gram per kilogram of air. So it has water vapor in tiny concentration. It has tiny water droplets, which are even in even smaller concentration. It is very, very turbulent. Clouds are very turbulent. If you've flown through any cloud, you're likely to have to wear your seatbelt immediately. So then clouds contain aerosol particles, which we will not be talking about today, and there's temperature variations within a cloud. So we are going to talk about one kind of instability which comes out of sedimentation from the cloud base. And then we are also going to talk about sedimentation in a completely different context. This is an experiment we did along with some theory to go with it. Basically, we have a big box of about this size and we drop discs like this through it. We have a mechanism to push the discs through, and these are falling into very, very viscous fluids. So in both of these situations, the droplets are in Stokes flow here and the particles are in Stokes flow here. So hopefully, the kind of instabilities we see and the kind of physics that comes out of it is going to have applications well beyond just a cloud or just, this lab experiment. So what are Mammatus clouds? The title talks about Mammatus clouds. So you see that these are bulbous shapes basically hanging from the cloud base. So the cloud itself has this very, the cloud itself looks, with these very bulbous and regular overhangings. They're called Mammatus because mamma is one of the words for one of the meanings of mamma is breast. So basically, you can see them in neat rows, sometimes not in such neat rows. But once you start recognizing Mammatus clouds, you can actually see them. So we call them, they're called not rare but serendipitous. So in other words, you can't be ready for, oh, today is going to be a Mammatus cloud day. You can't really tell when you're going to see them. So, but once you become conscious of them, you can see them, and they're really, really beautiful structures in the sky. The other kind of cloud we want to talk about are related, but they look very different. So these are called asperitas clouds, and after something like 60 years, when not a single new cloud was identified, in 2017, the World Meteorological Organization designated a new cloud type called asperitas. So these are the newest clouds, and the nice thing is there's like precisely one paper before ours which kind of talks about the fluid mech of it. So there's lots to be done there. So this cloud, we'll see how it's related to the Mammatus, but this is what the WMO says about this cloud. So the important phrase here is as if you're viewing a roughened sea surface from below. So that's a good way to recognize asperitas clouds. Sometimes they have these pointy, lobby structures which remind you of Mammatus, and sometimes they have, more undulating things, but these can be distinguished from all other types of cloud once you get used to it. Yes.
Are they related all to the topography?
Topography of
The earth?
No. You can see Mammatus in like many places, and same with asperitas. Asperitas are a bit rarer, and we'll see why, but it has nothing to do with the topography of the earth. It's like coming from above, as we shall see. Okay, so I talked about a cumulonimbus anvil. So this is basically what it looks like. These are, huge towering clouds which, when there's heavy convection in the tropics especially, and also in the extratropics, these rise from the ground to a very great height, like beyond 10 kilometers sometimes. And then what happens is that when this cloud water rises, so clouds are basically this mainly air, but water vapor that I told you about. And because they're lighter than the surroundings, they may be a little lighter than the surroundings because they're warmer and because they contain water vapor, they're rising up into the atmosphere. So like what happens is at some height in the atmosphere, their density matches the atmospheric density, because the density in the atmosphere keeps going down as you go up. So wherever that density matches the atmospheric density, they start spreading out laterally, because up above them it's even lighter air. So then they spread out like a gravity wave kind of thing. And so this kind of structure happens all the time, and these are called anvils. And anvils can happen not just in cumulonimbus, but many other cloud varieties. And they need not happen at the tropopause. At the tropopause, they're very likely because there's temperature inversion, but elsewhere also you find that there are these anvils. The important take-home thing is that these are stably stratified. So like this thing is lighter than this thing, which is why it's spread out there, and therefore like you will not expect instabilities. So why does it go unstable? That's the question we're going to ask. And these are what the Mammatus look like. Okay, so let's talk about a bit of history. Again, like there isn't a lot of work done on Mammatus clouds. There's very few fluid mechanics works, but people have been discussing verbally many different possible mechanisms. So the whole list of all the mechanisms is given in this paper by Schultz. It's really worth reading. And this paper tells us about that paper, which is in German or something. I think I couldn't read it, but it tells us that about 100 years ago, somebody came up with the same mechanism that I'm going to propose today. So it was proposed verbally as one among many plausible mechanisms, evaporative cooling, which is what we will come to. And since 1944, there's been some interest in making aircraft measurements. So people, whenever they saw Mammatus, they've been trying to fly through it. And by the way, this is a 747, and the size, relative sizes are like this. So the Mammatus lobe could be much bigger than this, or around here. So this is what it looks like. So then people have been trying to measure things like temperature inside, and but there's very few measurements. Of course, like radio sound and radar measurements, there's lots, satellite measurements, but we still don't understand what forms them. One mechanism was proposed by Emmanuel in 1981, Kerry Emmanuel, who said it could be a cloud-based deep rainment instability. So basically he said there's cool, warm, wet air above warm, dry air, and somehow if you're able to set in some mixing there, then such instabilities can form. And then there's precisely one simulation before ours that we could find. And in this simulation, they basically fed in the initial conditions that were observed just before the cloud Mammatus formed, and that we believe led to the Mammatus lobes that they noticed. And these things last for about 10 minutes. Okay, so what we do is we take a box like that, which is drawn here, and we do simulations in this box. This is joint work with Eckhart Mayberg and S. Ravichandran. S. Ravichandran is my former student who is soon going to join IIT Bombay as faculty. So we defined this box where there is cloud fluid. Even if we start it at 0 velocity, it becomes turbulent very quickly. And this cloud fluid contains saturated vapor, and it also contains droplets of liquid water. And below it is initially quiet and stays quiet for almost all the time below in this regime. Both of them are at temperature T0. It's stably stratified with this being slightly lighter than this. And we set the simulation with small perturbations there, and we let it go. So let's see what happens. Okay, so first of all, the first thing that happens is that, the first thing that happens is there are droplets of liquid water, which you remember are 1,000 times heavier than air. So they're going to start sedimenting. So the first thing that happens is these start sedimenting, and then as they start sedimenting, let's look at a single drop. So below the cloud anvil, it started falling. It had an initial radius of A0, and whatever its radius A at a given time, it's a tiny droplet, like, you know, tens of microns. It's going to be typically in Stokes flow. So then it will have a terminal velocity, which goes in this way as its radius. And as it falls down, it's evaporating, so its radius is coming down. And so you can see that the terminal velocity is also going to change. And this is the falling droplet that we're going to talk about. And the droplet evaporates according to the Clausius-Clapeyron equation, which after some algebra you can show just satisfies this equation, where S is the supersaturation. So in dry air, S would be 0, and dA by dt is just A dA by dt is minus of a constant. So you can actually, if the air stays dry, which it doesn't, you can very quickly calculate the radius and the distance that it can travel. So you can ask, like, how big does a drop need to be before it reaches the ground? Is it going to evaporate before it reaches the ground, or is it going to reach the ground? So like you can come up with a 1 millimeter droplet will reach the ground, whereas a 25 micron droplet, if it's super lucky, will stay alive for 3 seconds after it fell away from the cloud anvil, and it will travel about this distance before it totally vanishes. So here you have a whole bunch of very small droplets. In a cloud, there's a big droplet size distribution, and tens of microns is very likely compared to 1 millimeter. So those droplets are, you know, continuously sedimenting out of the cloud, and they're all traveling some short distance before they evaporate. Now the point is, as they evaporate, the air becomes wetter and cooler. So there's water vapor now in the air, and because of latent heat, the temperature is falling in the air. And this thing is going to be crucial to our mechanism. And then as more and more fall, they're not falling into dry air. They're falling into wet air, and they can travel longer before they die. So they can actually increase the size of this cool wet layer below the cloud. Is it clear so far? Okay, so now the equations that we solved. So there is this code which is called Megha 5, where Megha means cloud. It's developed, it's a beautiful code which runs in parallel, and Ravichandran, my co-author, had a big hand in developing this code. So the equations we're solving are the Navier-Stokes under the Boussinesq approximation, where theta is temperature differences, and RV and RL are measures of the concentration of liquid and vapor, and they each contribute to the density differences. So liquid droplets are heavier, and vapor is lighter than air, and then there's temperature. So then these three things contribute to the buoyancy, and that goes into the Navier-Stokes with a Froude number square in the denominator. That's the standard thing. Now here the thing to remember is that the latent heat given away is so much that latent heat is the winner. Like I could throw away these two terms and it wouldn't make a difference. If I retain theta, I would get the answer. So everything is dominated by temperature over here. So this thing differentiates it from all other sedimentation mechanisms. So in all other standard sedimentation instabilities, what happens is that a large mass of solid or particles fall into a lighter region, and because the solids themselves are so very heavy, they create an instability by creating a density overhang. But that's not possible for us because our droplets are so few and so dilute that their mass is not going to create any instability or any standard sedimentation behavior. It's yes. Somebody had a question? Okay, so here everything is happening because of the temperature, and that's the basic mechanism. So this is the temperature equation. So this part of the temperature equation you're used to, but here is a latent heat coming out due to evaporation. So this represents evaporative cooling, where theta is a non-dimensional temperature. The vapor concentration has a similar equation, except that now when there's evaporation, vapor is added to, and in the liquid concentration, an equal amount of fluid is vanishing from liquid phase and going into vapor phase. So these are the source terms. And the important difference here is this term, the Vp times del rho, del RL by del Z. Basically, Vp is the term. Can everybody mute yourselves in case somebody is not muted? What?
It just woke everybody up in the audience.
Oh, you mean I put you to sleep?
That was good.
Ouch. Ouch, ouch. Okay. Yeah, so Vp is the terminal velocity with which particles are falling, the droplets are falling. And Vp itself is a function of time. Remember in the last, in the last slide, we saw that it's proportional to a square. So this itself is a function of time. And now, like, you can see that this settling term, so I have to live in the frame of reference of the falling body, falling particles, in order to see evaporation, and which is where this term comes from. In other words, the U dot gradu is actually V dot gradu of the particles. So that's why this extra term comes in. And now the R, V, and L, I said they're proportional to the basic concentrations of the vapor and liquid. And another thing to remember is that 4/3 pi a cube is the volume of each drop, where A could be different. And if there are n such drops, then that would be giving my liquid concentration. So we have to remember that all these things are functions of time. So these equations are different primarily because of this term. So that's the new thing that's coming in here. And the evaporation is given by Clausius-Clapeyron, where H is not the Heaviside function. It is 1 most of the time, unless there's no liquid, in which case it's 0. So then there is a time constant of evaporation sitting in this, and you will see that, things like the number of drops, their radii, all of this comes into the time constant of evaporation. So like there is, time varying coefficients everywhere. So that's to be remembered. And this is just Clausius-Clapeyron, which tells me what is the saturation vapor pressure at a given temperature. So evaporation occurs if air is dry and condensation occurs if air is wet. It's as simple as that. The four non-dimensional numbers are latent heat, non-dimensionalized, Clausius-Clapeyron thingy, non-dimensionalized, fluid number, and Reynolds number. Okay, so what's the basic mechanism? We started out with something light there and something heavy here. And what happened is, as you have sedimentation through this layer, there is evaporation, and the subcloud layer cools a lot. And because of this cooling, by a lot I mean a few degrees, 2 or 3 degrees, that's what happens. And you get this density overhang. Once you get a density overhang, you're going to get Rayleigh-Taylor type instability, which is what creates the Mammatus cloud and also the asperitas cloud. So this is different from other sedimentation instabilities, as I told you. So let's look at some typical results from our two-dimensional simulations. So we let that happen, and we do see these instabilities progress. And in this panel, I've shown liquid, which was, a flat surface at time equal to 0, but this is at later and later time. And no, these are not at later and later time. These are different times for different initial radii. So each row is different initial radii, and at some typical time we plotted these things. So then the temperature, you can see the evaporative cooling. Wherever there is vapor, there was no vapor before, right? We started with dry air. Wherever there is vapor, there is corresponding evaporative cooling. And you see that as the initial droplet size increases, the lobes become more pronounced. Yes, Edris? Yes. Yes. Just to make life easy, we started them all out as A, and then we started with the number N. But as time progresses, depending on where evaporation is taking place, they're going to have a size distribution. And that's going to come out naturally, and in each grid, there's going to be a typical size distribution for the droplets. So we could have started with, a distribution, it wouldn't have made a difference. Okay, so smaller droplets don't quite do Mammatus. They give rise to these leaky structures. Remember, this is temperature, this is water vapor, but what you're going to see is liquid water in the cloud, and you will not see Mammatus if you have a whole lot of small droplets. So one of the things we find is that you need large droplets and you need a larger liquid content so that the overhang is sufficient. So we can do these calculations and come up with limits. Here I'm going to show you a three-dimensional simulation, and which I actually don't need to show you because it's very similar to the two-dimensional. So whether you do it in 2D or 3D, and here we've actually put the sinusoidal perturbation, so we've cheated a little bit, but you get these clean Mammatus structures. So this is just one typical simulation of a Mammatus. We have like Mammatus simulations of different shapes in different scenarios. So I just wanted to show you one typical one. Want to play it again? You have a question? Okay. Okay, so these are with smaller droplets but high liquid water content, and you can see that initially it all looks very rough, but with time it kind of organizes into lobes. Although these lobes are not as beautiful as in the big droplet case, you still see some lobe structure, and some of the irregular appearances of Mammatus look like this visually. That's the only thing we can say right now. So yeah, that basically we feel is the mechanism for a Mammatus cloud, density overhang created by the thermodynamics of phase change. And now, like, what happens? What are asperitas clouds? And this is our again our contention. I should say here that so many different mechanisms have been given in the literature, but they're all like argued for on some physical thought experiment basis. So like it could well be that one of those is the right mechanism for a range of Mammatus and asperitas cloud formation. But here we have a mechanism which seems to work. It seems to actually, you know, work both numbers wise as well as physics wise. So it's our contention that you take the same box as before with cloud above, ambient below, and add a shear to it, a uniform shear, and you get asperitas instead of Mammatus. So we do the exact same simulation, but now with a mean shear given by, you know, some numbers similar to observations of asperitas. And so if we do the exact same simulation, liquid water temperature, water vapor at the same time with zero shear and shear equal to 0.2, you see Mammatus-like structures without shear, and you see asperitas-like structures with shear, like a lot more smooth, you know, variation in this way. This is a two-dimensional simulation. So the small scales here, the pointy things are killed off every time you add shear. And one more interesting thing is we are able to see states which last forever, which never happened in Mammatus. Mammatus is a dynamically growing thing, and after 10 minutes it will die, whereas these sometimes can last for a lot longer because you get this nonlinear saturation where things keep coming from above and the shear keeps pushing it, and this shape goes nowhere. The shape stays as it is for a long time. So so here 3D is different. You can see some typical asperitas here. I just brought that in so that you may see similarities between the structures we have forming, which have a broad direction in this, they have a broad, you know, organization in this direction where the shear is going like this. So there's a span-wise organization. So if I play that again, you can see at some intermediate time, things which look like this, things which look like this, to a mother's loving eye. There, see. Yeah. So that is asperitas. They look different under strong shear, weak shear, and intermediate shear. So these are just some examples. And if we use very high shear rates, asperitas disappears. Shear stabilizes. So the minute you have shear, you need some very narrow range of shear, which is going to make it happen. And as I told you, in this asperitas, there's been only one paper. They argue for some gravity wave trapping because of the way the cloud can be stratified, but that's it's possible that that mechanism is correct, but because this is all so early in the game, we can't say what is happening. Okay, so we just did a linear stability to confirm all the things. So we ran the simulation in 1 dimension and time. We obtained the density overhang for a whole variety of conditions. You can write out the stability equations, and with appropriate grid stretching in this direction, in this regime, if you put enough grids there, you can actually get reliable stability answers. We always get standing waves which are growing in time, and so standing means they're not moving in the horizontal direction. So then under different conditions, we get different wave numbers of growth, which are broadly consistent with our simulations. So we do this very simple stability analysis, but we haven't included thermodynamics in the stability, which we need to. So my basic remarks on this part are the following. We seem to have a plausible mechanism and also evidence in terms of some quantitative features for Mammatus and asperitas cloud formation. I'd like to emphasize that we did all our simulations at a Reynolds of 1000, which is what we could do in our 3D box. And before we say anything about clouds, we need to do this at far, far higher Reynolds numbers. And the broad thing is that can we go in this thought process? Can we take this thought process further? Can we take this kind of physics further to understand other kinds of cloud patterns? So like that is one way in which we can think further. Another thing, and this is for you, Laurette. So this thing is, it's worth generalizing the concepts we know from thermohaline instabilities, because there we have two species which are diffusing very differently, right? Here we have multiple species. We have water vapor, temperature, we have actual droplets. We have multiple species diffusing, and in various chemical industry and other situations like sprays and all, we may have even more species diffusing. And right now we took the Prandtl number and Schmidt number as one, but depending on the situation, those things may be vastly different. Secondly, the dynamics of these droplets, their Schmidt number is effectively infinity. So they don't diffuse at all, but two droplets could be doing random walk and diffusing at some completely other rate. And then like when all of these are sedimenting, the one important thing is that there's production terms everywhere. There is, that's what differentiates it from the standard thermohaline instabilities that we know about. So there's a lot of other things which may be relevant in this kind of thinking. Yes.
That the background flow, for example, the strong shear flow horizontally, would affect the patterns as well, or not at all?
So like this is the effect of the shear. This is the effect of the background shear. This is without shear and with shear. So like here, I mean, all of this is at Reynolds of 1000. So it's still turbulent, but this is what we can say.
That's the follow-up question. What happens if Mr. Taylor co-op with shear?
If
Rayleigh-Taylor with shear.
okay, so Rayleigh-Taylor with shear typically shear stabilizes.
You get the same wavelength that you were seeing for the instability, or is it?
So like in effect, the stability analysis we've done is we've taken this density overhang and we're effectively doing Rayleigh-Taylor with shear. And we're getting some ballpark comparison, but not, yeah. The only thing is that, and we also get the same concept that if you have a very strong shear, as you increase the shear, the instability goes away. So like all of these are broadly in, aligned with Rayleigh-Taylor.
Can I just ask, can you show me that movie one more time?
Okay.
It takes me a while to get my eyes, not that one, the previous one.
Yeah, I love this movie, so I'm very happy to show it again.
So, can I understand, you put in the length scale in one direction, but not in both directions?
We put it in both directions.
It's in both directions.
Yeah.
So we can't deduce that it selected a square pattern.
No.
Okay.
No, it didn't select the square pattern. We by hand put the square pattern, but this shape has come out. We didn't do anything. I mean, this is not like Rayleigh-Taylor. This shape has come out of, nothing we did. And in this situation, we put some other wave number, but it selected, it slowly became bigger and bigger. These things got organized into larger structures with time. So we've done simulations where we by hand put wavelengths, and we've done simulations where we don't, and still you get some kind of organization, but not as beautiful as the other one. Other questions?
Sorry, Rama, can you hear me?
Yeah, I can hear you.
Yes, I'm Dario. Sorry, could you please move the microphone a bit farther from the mouth, because the sound is highly distorted.
Sorry.
No, my apologies for this interruption.
No, to tell you the truth, this is a gender biased mic. It has, so I had to wear it high up, but now I've pushed it down. Is that better, Dario?
Yes, it is. Thanks a lot.
Okay, sorry about that.
Thank you.
Okay.
Just to clarify, your droplets, they're just vertically falling with a terminal below
That's correct.
There is no other complicated motion
No.
so it doesn't even depend on the size of the droplet, the way it's falling.
Yeah.
In the terminals.
Yeah.
So no preferential sweeping of wet and dry.
Nothing.
No going back because there's turbulence.
Right. So they are not, I mean, their inertia is only in the sedimenting.
Only
Yeah.
determining the wetting velocity.
Yeah. And here the logic or the thing that we argue is that below the cloud base, there's no turbulence. It's all quiet. Remember, you weren't wearing your seatbelt till you went in. So here it's all quiet. So everything is just falling, raining quietly.
If there was a wind shear, of course, it would be slightly different.
Yeah, yeah. If there was a wind shear, it would be different. There would be turbulence. You can't escape that.
Or even if it's a smooth but random.
Yeah, yeah, yeah. So yeah, I mean, it's the assumption we have that it's all quiet below, and they. But of course, like falling vertically is a poor assumption, which is what I'm coming to in my next thing. We said that the assumption so far, we have spherical particles. Ice particles are often not spherical, and often Mammatus forms from ice particles. So that's not good. And we talked about one-way coupling. By one-way coupling, we mean that the fluid doesn't get affected by the particles only get affected by the fluid. So like these particles are just falling quietly, they don't know about each other, they're not clumping, they're not doing anything, but we know that sedimentation is always subject to clumping, and I'm coming to that. So just to think of them as falling vertically in straight lines is not a good assumption, even in a dilute suspension, because even if they're relatively far away from each other, the Stokes, field that streamlines that they'll be creating only decay as 1/r. So they, like, particles can feel each other even if the interparticle distance is much bigger than their radius. So then it's important to ask what happens when particles interact and when they're not spherical, which brings me to the experiment I told you. There were discs falling in a viscous fluid. So that's what we're going to talk about. So what happens is when there are two particles separated by r, instead of each falling at its terminal velocity, they fall together faster because the drag in the middle region is reduced, so they fall faster. If two particles started out like this, spherical particles, they'll fall in this direction. They won't fall vertically. So all of this will happen. And there is the famous Crowley instability, which was proposed in 1971. Which says that because of this interparticle interaction, particles have to inexorably clump. They can't do anything except clump, so long as they're spherical. So clumping is inevitable. That's the story behind the Crowley instability. So the story is very easy to see, because if there are two particles in Stokes law, they're going to fall, they're going to travel in this line, and two particles are going to travel in this line. So what do three do? The middle one will go vertical because it gets its lateral motion gets cancelled, but these two guys come closer to each other. It's as simple as that. So whatever you may do, it is going to clump all the time. And that is Crowley instability. So now we asked what happens to ellipsoids. So we look at basic interactions between ellipsoids, and we are writing the far field forces up to A by R, where R is the distance between them and A is each one's typical radius. So here we've taken the bigger radius. And all of them, like when there are two ellipsoids, they put some X or horizontal motion on each other, even when they're falling vertically, and that's given by this expression. They also rotate each other. So their rotation is given by that expression. Sorry, like theta up to now was temperature, but forget that. Right now, theta is the orientation. So they're going to rotate also. So that is going to happen in these. So like now we are talking about interacting, sedimenting, Stokesian discs. I showed you this picture already, where we have silicone oil in a big box, and we in our lab we're pushing through these 3D printed little resin particles, which are slightly denser than the silicone oil, and they're falling in that oil. So this is the work of Rahul Chajwa, his PhD work. He survived me and 2 other advisors, and he's now a postdoc in Stanford. So yeah, and the story is the following. We asked, do we have to have this clumping instability? Can shape make it not clump? That's the basic question we were asking. So like I described this thing to you that, you know, whenever there's like particles in a row, like any place where they're coming slightly closer together or one is slightly below. So any perturbation of this kind is going to create clumping automatically. That's Crowley. So what happens in ellipsoids? The interesting thing is that again, you get this clumping, and then you get this falling, but then that goes accompanied by rotation. So once you get this clumping, you're going to get rotation. So these two are going to face this way. And the minute an ellipsoid faces this way, its Stokesian behavior will be to go away. So like rather than clumping, it has a tendency to go away. So there is this clumping due to this force, and then there is this tendency to go away due to its own orientation. So like, can particle orientation counteract the Crowley instability? And I'm going to show you a movie which seems to say no, but wait. Right now you'll see the Crowley kind of instability in ellipsoids. Do you see that movie? Do you see the clumping? And you can actually like write down nearest neighbor Stokes theory, and our theory matches with our experiment like every time, including quantitatively, it matches perfectly. So that's the beauty of this experiment. So very clean experiment by Rahul. So what do? We can write down, like if we start out with this in a line, and we can put in some initial perturbations, like, you know, we have many slots in our thing which a comb then pushes through. So we can choose which slot to put a disk in, and we can create, you know, little perturbations of the wavelength we choose by this. And it's of course discrete perturbations. We can't always put the optimal perturbation or something. And these are the equations. Here U and Ux and Uz are the horizontal and vertical displacement, not velocity. And each particle's displacement is given by the location and orientation of all its neighbors. And then we pretend that only the nearest neighbor is going to change its dynamics. We linearize this, Fourier transform in X, and we take nearest neighbor interactions. And then by re-normalizing the U and X and UZ and calling them U and W, remember they're now displacements, not velocities, and re-normalizing the orientation, we can write this very nice little matrix which describes the dynamics in the linear limit. Remember, it's non-linear because there are sine 2 thetas and sine theta squares and so on. So then this is the matrix which describes the dynamics of these disks. So you can see that this is a non-normal matrix. And what does that bring us? We will see. So now we were asking the question, is clumping inevitable? Do we always have to have clumping, or is there a region where the thing can be stabilized by orientation? And we will see that yes, it can be stabilized by orientation, but the fact that it's non-normal is going to play a role. So this is what it looks like. So here are the wave numbers and here are the lattice spacings. And this blue color, if you can see, is theory which shows the stable region. And this pink region is unstable by theory. So this is the line like dividing the theory from the theoretical unstable and stable boundary is there. And these dots are all experiments. So you can see a beautiful matching between theory and experiments in this case. So what happens in the stable regime and what happens in the unstable regime? This is what we'll see. And this is actually the experiment, a photo of the experiment at a particular, different time lapse things of the experiment. from this point where it was all stable. So you see more or less a wave-like behavior, oscillatory behavior. And this dot here looks like this. The Crowley type of instability has come up in this. So then, yeah, in that thing, I told you it's non-normal. So we can look for algebraic growth. And this is what the algebraic growth, the maximum growth looks like in that same plane. So over here, there's very little algebraic growth. And over here, there's quite a lot of algebraic growth in the stable region. So like different kinds of behavior can be expected in the stable region. So this is just disks falling, remember. And now, if we do a linear computation, let's say somewhere here, this has been done somewhere here in the weakly growing region. I called it algebraic growth, not transient growth, for an important reason. The thing is that this growth, the non-exponential growth, is actually strictly periodic in this case. So this algebraic growth goes up and down, up and down. That's what it looks like. So you can get a gain in energy from time to time. Remember that if the matrix was normal, you would have a gain of 1 max. You will never get a gain bigger than 1. Questions? Okay. Sorry? Where does what? Basically, from these equations. Yeah, basically there's 3 eigenvalues. One is 0 and the others are plus or minus some frequency. So like in the stable region, it's just oscillating with some plus or minus frequency. So after 2 pi over that frequency, after that much time, the whole system will return to where it was. This one? Basically, it's the Crowley one. It's these things beating against each other. So this lambda is the unstable part and this is the stabilizing part. So basically, if you solve this system, there's no other option except to return to a particular configuration after a big time t. Of course, remember this is linear. If it's non-linear, it may not return. Okay. Okay, now, interestingly, this matrix can be split into 2 normal matrices. So I just wrote down normal plus normal equal to non-normal, just for fun. But yeah, this is normal and this is normal. So if you see U and W beating against each other, it's the standard Crowley instability where there was no orientation. The orientation theta did not play a role. So this thing is always going to give you a 1 unstable eigenvalue and that's all it does. So, and there is no non-normality there. It's plain old exponential growth. Now, if I throw away W, like just if I pretend that there is no vertical displacement, I somehow force the vertical displacement to be 0. Then the way U and theta beat against each other is analogous to a spring mass system. And we can do lots of interesting stuff with this. Like there is even Hamiltonian dynamics and stuff, which I won't go into. You can do, I mean, it will take us too far away. You can do lots of interesting things with this thing. There again, like a spring mass system, it's only going to beat against each other and it's going to be neutral. There's going to be no fun there. But put them together in this combination and you see very interesting transient growth behavior. So this is a movie. Yeah, it's actually, oops. So now I'll just quickly show a few movies which will play. And this is just the initial wave-like behavior. This is actually from the experiment. That thing is just a movie of the experiment. And we can do numerics, which will do exactly the same thing. So you see the wave coming and going slowly at early times. And now this is when you have a thing which is so-called neutrally stable, but it gets driven at late times to non-linearity. This is also experiment. Except for these little thingies at the bottom, you can't tell the experiment from the simulation. Yeah, so you see some level of clumping, but it's a different kind of clumping. And we're trying to understand this different kind of clumping. And Harshit Joshi is a new student who's working for his PhD on this problem. And I could have put a photo of Shamriddhi, but the real person is there. I can't point the laser at you, but you're there. So like, yeah, no photo for him. Yeah. So we are trying to understand clumping behavior together and see like whether we can take it to some other ellipsoid, ice formation and some other kinds of applications. So I'll just show these two movies which show a different kind of clumping. This is exponential growth and this is algebraic growth. So you see the signature Crowley thing, but then they do and some interesting stuff, some interesting nonlinear stuff. And this movie is just like simple wave-like behavior for a long time, but then with the transient, with the algebraic growth, nonlinearities take over. And I don't know how to fast forward it, so let's watch it till the end. Or maybe I can fast forward it a bit. Yeah, it's nice to see the way these things dance. Three of them come together, then go away. So the way orientation plays, like, then these three start interacting and then those three don't. So the way orientation makes them move in this way and interact differently till finally nonlinearity takes over. So the clumping behavior is different. So we've shown that transient growth leads to a different kind of clumping. So here we take three different locations on this wave number and distance between particles plane. And one is unstable, which the movie you saw just now creates a lot of clumping. And the other is stable, but with no transient growth, no algebraic growth. And those just go in straight line with nothing at all happening. So in that regime, we can fully stabilize these things with no clumping. And then there's this intermediate regime where we saw weak clumping. So this is the kind of nonlinear behavior that comes out of this. So that's basically all I wanted to say today. So like the moral is that sedimentation needs to be studied further. So these are two initial studies in these two directions. And already we see that there's a lot of rich behavior in this. Even in the linear limit, there's things which can be looked into further. So whenever you take sedimentation and you combine it with the thermodynamics of phase change, interparticle interactions, mean shear, and of course turbulence. So when you do all these things, you're going to get new physics out of this. It need not just be sedimentation. It could also be particles which are going along in a gravity wave and how they interact. It could be a variety of such things. So while all of this we talked about has applications to clouds, it can have very important applications in industry and in so many other geophysical situations. So thanks for your attention.
Fascinating talk. Questions? I think I need to use the mic. Questions from the audience.
Thanks, Rama, for this really beautiful talk. My understanding, at least from a little bit, that you spoke mostly about what people call sometimes warm clouds, in a sense that they don't include snow or ice. So is there anything that you can maybe short comment about what happens in case clouds contain also ice in them?
Yeah.
So the dynamics will be much more complicated, and then it's not only particle of droplets, but there's also particles of ice or something.
Yeah. So basically, as far as the thermodynamics is concerned, if you have very teeny tiny ice particles or water droplets, it's going to make no difference. because the latent heat of ice going to water is much smaller than water going to water vapor. So there'll be a little extra latent heat and this thing may be accentuated, but beyond that, nothing is going to happen so long as everything is very, very tiny. But if things start clumping and you get bigger and bigger ice crystals, then like you have to look for things like clumping behavior, things like how they interact with each other, which we just want, I mean, did the simplest thing in order to understand what's going to happen in that. So like those will need to be studied in greater detail, which is what Harshit will do with Shamriddhi and me, but it's not just us, it's a very, very big area, like it's ripe for a lot of people to work in. So then that will be one difference, the shape, because morphology of ice crystals is very, very different. The other big difference is going to come when these grow very much. And if they've grown to a bigger size, you can't pretend they're in Stokes flow anymore. So then like you have to have corrections for high Reynolds number flow of the object itself. And that will be interesting add-on to this. Because how they recruit things in their wake, many other such things happen.
Okay, any other comments, questions?
Can I get anything from this drama about cloud seeding, trying to make it rain?
Okay, not from this, but what happens is that you need aerosol particles. I glossed over that. You need aerosol particles to make clouds. So like suppose you don't have any aerosol particles whatsoever, you cannot have condensation and you cannot have rain. So here when we said, you know, we put a function which said if the liquid is zero, then it's going to, if the liquid is not going zero, then it's going to condense. We've assumed that there are enough aerosol particles around. So like first thing is, if there's no aerosol particle, there is no rain. So in cloud seeding, you just add to the number of aerosol particles. And you make hygroscopic ones, like you put silver iodide or something which likes water and it, you know, water droplets condense on these things and then you can create artificial rain.
Yes. You said that your 3D code had a Reynolds number about 1,000. What actually would be the typical Reynolds number in a cloud?
Oh, in a big cloud, so it could be 10 million
Yes.
of that order. Even in the, if I want to compute a single Mammatus lobe, it could be of the order of 1 million,
Right.
no less.
Okay. All right.
So like to give you an idea, the Kolmogorov scale is less than 1 millimeter.
Mhm.
And we want to do something which is 1 kilometer. So that's 10 to the 6 already. So,
Okay. Thank you.
yeah.
The large scale Reynolds, right, Rama?
The large scale, if I want to compute a full Mammatus blob at the correct
Number you
Reynolds.
were saying was the large scale Reynolds number.
Yeah, yeah,
So
large
the
scale
Taylor
Reynolds.
scale would be
The large scale Reynolds number, the particle Reynolds number is very small. It depends on the relative velocity between the particle and the fluid, which is typically very, very small.
Any other questions? I can see some refreshments out in the hall. I just checked as I walked past. Oh, yes. Good point. Anybody online? I can't actually see who's, but any hands are up. Anybody online want to ask a question? Please unmute yourself and go ahead.